You've seen how the mean of a data set gives you important information about the population the data comes from. In the case of probability, the mean has a similar purpose and gives important information related to the likelihood of certain events. Let's start with an example. This table shows the probability distribution for a fair die. The probability of the die landing on any of the values from 1 to 6 is 1/6. What is the mean of this probability distribution? The mean of a probability distribution is a kind of weighted mean. The weighting comes from the values of the probabilities themselves. This is the formula for the mean of a probability distribution. The sigma here indicates that this is a sum of terms. Each term is the product of the probability and the value associated with the outcome. Let's look at the mean of this probability distribution. The first term is the product of this number, 1, and this probability, 1/6. This is added to the product of this number, 2, and this probability, 1/6, and so on. These are all the terms. Notice that each term has 6 in the denominator. We can rewrite it this way. In this form, you can see that this form is the same as the mean of the numbers on the die divided by 6. The result is 3.5. This is the mean of the probability distribution. It is also known as the expected value. Now, we know that if we roll a fair die, it will never land on 3.5. There is no square on the die that has this value. So what does this expected value mean? If you were to roll the die, say 50 times, and record the outcomes in a table, the mean of those outcomes would be close to this expected value. Let's look at another example. This table shows the probability distribution for 2 dice and the sum of the numbers on each die. There are 11 possible outcomes, each with its own probability. What is the mean of this probability distribution? As before, find the weighted mean by multiplying by its corresponding probability. You end up with this long expression. Once again, notice that each term has 36 in the denominator. Rewrite the expression to get this. We end up with 252 over 36, which equals 7. This expected value is a little easier to understand. Looking at the table, you can see that the highest probability is associated with a sum of 7. So when rolling 2 dice, the expected value aligns with that. One other thing to notice is this. Recall that the expected value for a single die was 3.5. So the expected value for 2 dice is simply the sum of 2 expected values for each of the separate dice. Let's look at a final example. This is the probability distribution for flipping 3 coins and counting how many coins landed on heads. Use the graph to find the mean of the probability distribution. Use the graph to extract the data to plug into the mean formula, as shown here. Multiply 0 by 1/8, as shown here, 1 times 3/8, as shown here, 2 times 3/8, as shown here, and 3 times 1/8, as shown here. Simplifying the expression gets us these 3 fractions, which share a common denominator of 8. We get the improper fraction 12 over 8, which simplifies to 1.5. With 1.5 as the expected value, if you were to flip 3 coins multiple times and track the number of heads, the mean of your dataset should be close to 1.5.